Hi guys, so welcome to another lecture about drilling engineering. My name is Raj and today we will be discussing about drilling rig. So I'm sure you must have heard about this term drilling rig repeatedly. So what is a drilling rig? A drilling rig, we can say, is an integrated system which helps us to drill a well. Okay, and that well can be an oil well or a water well depending upon the rig which we are employing. So we are interested here in discussing about an oil drilling rig which is used for rotary drilling method. Okay, so there is often a misconception that the drilling rig is just a tower like structure which we can observe when we visit a oil field, but that is not true. This entire system, this entire combination of different equipments is known as your drilling rig, and using all this system we can drill a hole into the ground. So this is a machine, we can say, which is required for drilling a hole inside any formation. Okay, so this entire drilling rig is divided into different components. So we have 6 basic components: derrick and substructure, power system, hoisting system, rotary system, circulating system, and well control system. So any rig that you visit anywhere in the world, it may be any type of rig, you will always have these basic components. So we will see one by one each component. In this chapter we will be going into details about each component, but in today's lecture I'll be just giving an overview about the drilling rig system. Okay, so the first one is derrick and substructure. So as you can see, this is known as derrick and this is known as substructure. So derrick is basically the mobile tower like structure that you observe when you visit a oil rig. Okay, an oil rig. So this structure, this tower like structure is known as derrick. Okay, and derrick stands on the rig floor. So this portion is known as rig floor. So the derrick will stand on the rig floor, and below the rig floor is the substructure. Now what is the importance of this derrick? So this derrick supports and provides the necessary height. Okay, first of all it provides the necessary height for the drilling process to continue, and then it supports the necessary weight required for the drilling process. So as you know, we will have to provide some weight in order to drill the formation, so that weight should be supported by this derrick. So everything will hang from this derrick itself. All the weights that are put inside the hole are hang from this derrick itself. So the derrick should be strong enough to carry those weight, and it also have to provide the necessary height. Okay, so why is it important to provide the necessary height? So as you know, you might have gone through it somewhere. So drilling is done in joints. Okay, joint means a single drill pipe. Okay, but tripping out is done in stands. Stand means one stand equal to 3 joints. Okay, so stand is a combination of 3 joints. So one joint basically has a height of 30 feet or length of 30 feet, and stand will have a minimum length of 90 feet. Okay, if we consider the general configurations. So while tripping out, we are taking the drill pipe out of the well in stands. Okay, so those stands height should be accommodated inside this derrick. So this derrick should have enough height. So it should have minimum of 90 feet. So it depends upon the size of the rig. It may have some lower heights and some more heights, but generally it should accommodate this stands while tripping out. So this is the necessary part of derrick. So it should be strong enough and it should have enough height. And then comes the rig floor. So on the rig floor, different processes take place. Okay, different processes take place, and we have different equipments on the rig floor. We'll be discussing about that. And below that rig floor is the substructure. This is the space below the rig floor is known as substructure. So that substructure is provided to accommodate different piece of equipments like BOP and wellhead. So this is ground, this is the ground. So the substructure should have enough height from the ground. That means the rig floor is placed at a particular height above the ground. This is ground, this is rig floor. and the space between rig floor and ground is known as substructure. So those were the first components. Second thing is power system. Okay, so like any other machine, this machine we can say also requires some amount of power to run. Okay, so that power is provided by this power system. So there are different types of power systems depending upon the way the power is transmitted and the way the power is generated. So some power systems, they will generate electricity. Some power system, they will directly transfer the power to the drilling rig, and the way in which the power is produced, that is also different from rig to rig. So there are different ways in generating the power and transferring the power. So the system which transfers the power by generating the power is known as power system in order to run this entire drilling rig. So that was your power system. Next comes the hoisting system. So the function of this hoisting system is to provide a means of lowering and lifting different components of the drilling rig, such as drill strings, then casings, and any other component. Okay, so the lifting and lowering part of the drilling process will be done by our hoisting system. Now what are the different components of hoisting system? So first of all, first component is crown block. So crown block is situated at the top part of at the topmost part of our derrick. Okay, topmost part of our derrick, and it is connected to another block which is known as travelling block. So crown block and travelling block, they are combination of pulleys. So these pulleys, you must have studied these pulleys in your higher secondary examinations. There are different problems based on these pulleys. So this crown block and this travelling block are nothing but they are combination of pulleys, and this rope is wrapped around the crown block and through the crown block to the travelling block. Okay, so this performs this combination of crown block, travelling block, and this drilling lines are known as block and tackle system, and they perform the task of lifting and lowering any piece of equipment which we need. So that is our hoisting system. So they will help us in the drilling process by lifting and lowering any piece of equipment we need. Okay, and they also help us in providing the weight on beat. The weight that is required for drilling the well is provided by this hoisting system, by allowing the weight of the entire drill string to fall on the formation. Okay, so that was our hoisting system. Now comes the rotary system. Now this travelling block has a hook attached to it. So a hook will be attached below the travelling block. Now this travelling block is connected to a piece of equipment which is known as swivel through this hook, which goes inside the bail of an swivel. Okay, so this is bail and this is a hook, so it will be connected like this. So above it is travelling block and below it is swivel. So swivel is a very interesting piece of equipment. It is a piece of equipment which provides pressure integrity and avoids any leakage by rotating the lower part and keeping the upper part stationary. So that means its upper part will remain stationary but its lower part will rotate. Okay, and it also provides seal so that there is no pressure or fluid leakage. So that is our swivel. Now swivel is connected to cali, which is connected to rotary table. So the actual rotary motion is generated by this rotary table. So the rotary table will generate the rotary motion and it will transfer it to master bushing. Okay, so master bushing is a piece of equipment which is placed inside the rotary table, and then master bushing will be connected to cali bushing. So master bushing will transfer rotary motion to cali bushing, and the cali bushing will transfer the rotary motion to cali, which is connected to the drill string and which is connected to the bit. So like that, the rotary motion from the rotary table will be transferred to the bit, and finally the formation will be cut. Okay, so that was our rotary system. Then comes our circulating system. So as you know, in a rotary drilling method or any other drilling method, some cuttings will be generated. So we now have to leave those cuttings out of the well up to the surface, and we have to discard those cuttings. So that is done by circulating system. So circulating system, inside a circulating system we will have a mud which will circulate and which will carry the cuttings out of the well, and they will discard it in the required space. Okay, so the circulating system includes these systems. So the cuttings which are generated will come out from the annulus between the drill string and the casing or drill string and the hole, and it will first enter the mud return line. So this line which is connected to the hole is known as mud return line. So from here the cuttings which are present inside the mud or the drilling fluid carrying the cuttings will return to the surface system through this mud return line, and they will first enter a manifold. Manifold is a combination of different valves and different pipes. Okay, so using the manifold we can control the path of our drilling fluid. Okay, so drilling fluid can be sent here, can be sent here, or can be sent here. So it is basically a combination of different paths, we can say. So from the manifold, if more amount of gas is present, it will go to the mud gas separator. From here gas will be separated, and then mud will again enter the mud treating system. So this is known as, this entire thing is known as mud treating system or mud treatment system. So the task of this entire system is to remove the cuttings from the drilling mud so that clean drilling mud can again be sent inside the formation. Now we have to remove the cuttings because drilling mud will have some kind of density. So these drill cuttings can affect those densities and rheological properties. Now what is rheological properties? These are the properties which control the internal structure of our drilling fluid, which we will be discussing in the drilling fluid chapter. So the cuttings, they can hamper or interfere with the density and the rheological properties of the drilling mud, which can in return hamper our drilling process. So the cuttings have to be removed. So we have a separate treating system just to remove those cuttings. So the drilling fluid carrying the cuttings will first enter the shell shaker. So here this inside this shell shaker you will have a screen, a vibrating screen. That screen will separate out the large cuttings. Okay, they will separate out the large cuttings from the drilling mud. Okay, now these cuttings will enter the earthen pit. Then from the shell shaker the drilling fluid will enter the degasser. Okay, and in this degasser gas will be separated out from the drilling fluid. Then the cuttings which were too small to be separated out in this shell shaker will enter the descender and the desilter. So descender and the desilter will filter out the finer solids which were not discarded at the shell shaker, and then finally after all the cuttings are discarded and put inside this earthen pit. Okay, so this is also known as mud pit. Here all the discarded portion of the mud is accumulated so that it doesn't harm the earth surface. Okay, then finally clean mud will enter the mud tank. From mud tank it will enter the suction tank. So this is suction tank. Okay, so whatever, if we need to change the mud property, we need to add something, we can add inside this system through this hooper. We can add whatever we want, some ingredients or some other additives that we need to add inside our drilling mud to change its properties into according to our requirements. We can add through this hopper, and finally the mud will enter the pumps. Okay, so these are reciprocating pumps. So these are positive displacement pumps which reciprocate in order to displace the mud inside the formation. So the mud has to enter very deep inside the formation. So we will be requiring high pressure pumps in order to push those mud inside those holes which are present at greater depths. So after the mud has entered these pumps, from these pumps, so generally 2 pumps are employed in a drilling rig, but you can also continue the process using 1 pump. So from these pumps, the mud will enter the flow line, and from the flow line it will enter a pipe which is connected to one of the legs of the derrick, stand pipe. This pipe is known as stand pipe. So this stand pipe will have a pressure gauge where the circulating pressure can be monitored. Now from the stand pipe, it will be connected to the rotary hose. So rotary hose is a rubber hose or rubber pipe which is connected to a gooseneck. Okay, so it is, the shape of this gooseneck is like this. Okay, so from the shape the name came, gooseneck, and gooseneck is connected to swivel. So drilling mud will enter the flow line, and through the flow line it will enter the stand pipe, and from the stand pipe the rotary hose, then this gooseneck, and from the gooseneck it will enter the swivel, and from the swivel it will enter the cali, and then inside it will go inside the drill string, and finally through the drill bit it will reach the bottom, and again this process will continue. So this is our circulating system. Then finally comes our well control system. So as you know, while drilling a well we can encounter some kicks. So those kicks, so that those kicks does not turn into a blowout, we have our well control system. So well control system is a combination of BOPs. So when time comes, this BOP can close the well so that the kick that we have encountered does not reach the surface and does not turn into a blowout. So these BOPs are controlled hydraulically. Now the hydraulic fluid is stored in cylinders inside the equipment which is known as accumulator. So they will have pressurized hydraulic fluid which can operate the BOP. Now below the BOP we have wellhead which supports the casings. Okay, now this is catwalk. So whenever we need to place a drill pipe inside the hole, so first the drill pipe will come here into the catwalk, then it will go to the pipe ram, and then it will enter the mouse hole. Okay, then we will disconnect this Kelly and the drill pipe which is already present inside the hole, and that Kelly will be connected to this pipe which is present in the mouse hole, and this pipe will be lifted, and again it will be stabbed into the pipe which is already present inside the hole. Okay, so like that pipes are added, and that is known as making a connection. And while tripping out the entire thing, that means the swivel, then the Kelly, all those things are placed inside this rat hole, and then the pipes are lifted up and they are stacked on the pipe stack which is present here. Now the pipes, while tripping out, the pipes are not placed on the ground, they are placed on the derrick itself. So in derrick we have a place to store those pipes in stands, and fingers are employed in order to store those pipes in support of the derrick. Okay, so like that while tripping out, those pipes are kept on the derrick itself so that they can be put inside the hole as soon as possible. Now this is I could not draw it properly, but this is a small room which is known as dog house, where the driller will be present, and he will monitor all the activities which are going on. He will control the brakes, he will control the rotary motion, everything, and he will also monitor the pressure, and the pressure, if it fluctuates, he will have some consoles here. So from those consoles he can observe the different fluctuations which are occurring, and he can take necessary actions. Now this crown block is connected to the drawworks through a fast line. So what is a drawwork? Drawwork is a piece of equipment which has a drum inside it. So on the drum, this drilling line or the fast line is wrapped. So as the drum rotates, the traveling block goes up and the drill string is lifted up, and if the drum rotates in the other direction, the traveling block will go down and the drill string will go down. And the other connection from the ground block to a ground or a rig floor is known as dead line. So this line doesn't move, the fast line will move up. It will go up and down, and this dead line will stay stationary. So if this is the extra piece of drilling line which we can use if some wear and tear happens inside this working part. So these are, we can say, reserve line. So with time we release some of the dead line from here, and here it is an anchor is present. So this anchor is fixed, so the drilling line is kept reserved. So if we need some extra drilling line, so some drilling line can be released from here and it will come in the working system. So this is done with time to time to prevent wear and tear and breakage of the drilling line. So this was an overview of the entire drilling rig. So there are also some other small equipments which I did not cover here, but basically you will have these 6 components in all the drilling rigs that you find. Okay, now moving ahead to the different types of drilling rigs. So let's discuss different types of rotary drilling rigs. So as you can see, the rotary drilling rig are divided into 2 types, or it can be broadly classified into 2 types: land rigs and marine rigs. So land rigs are the rigs which are used for the drilling operation on onshore, that is on land, and the marine rigs are the rigs which are used for offshore operations, that is the rigs which are employed on ocean. Now first coming to the land rigs, main design features of land rigs are operating depth and portability. So these 2 are the different design features. So based on these design features, we can again classify the land rigs in conventional types and mobile types. Now in conventional rigs, the rigs are built on site itself. In earlier days, when conventional rigs were more popular, they were built on the site itself, and after the drilling process was completed, they used to leave these conventional rigs on the site itself. Now that is a very expensive affair. So in order to avoid that, the idea of mobile rigs came into existence. Now mobile rigs can be transported from one portion of the earth to the other. So they are transportable, they are portable, so we can easily move them, and assembling them is also fast. Okay, we can assemble it within 1 or 2 days, but conventional rigs require more than 15 days to assemble. So among those portable rigs we have, among those mobile rigs we have portable mast and jackknife. Now jackknife is a type of portable rig which is assembled using pins and then raised from the ground. Okay, they will lay this jackknife rig on the ground, and they will have pin connections. Then they will connect all the pins and they will raise it to the top using a crane. So that is our jackknife. Then we have portable mast. This portable mast is generally skid mounted on trucks. That means they are attached at the back of a truck, and the truck can go from one place to another, and using that truck, this portable mast can be transported easily. And they can also, this is a telescopic rig which can also be raised in a very short period of time. But conventional rigs are more strong, and if we need to drill higher depths and high pressure and high temperature wells, then these are more preferable. But for a smaller project, we can use mobile drilling rigs containing portable mast and jackknife. So that was all about our land rigs. Now coming to the next rigs, which is marine rigs. Now again, the design features of marine rig include operating water depth, portability, okay. So these two are the design features of marine rigs. So based on these design features, again marine rigs can be classified into floating types and bottom supported types. So like a drilling rig, the marine rig can also be further classified. Now these bottom supported rigs are used in shallower depths. So what do we mean by bottom supported? So this is the water body, this is an ocean, okay. So this is our rig. So if the rig has some kind of support up to the seabed, then it will be known as bottom supported. And if it just floats without any support, just like a ship, then it will be known as floating rig. This has a support just like a bridge, and this has no support, just like a ship, okay. So this is bottom supported and this is floating. So bottom supported are generally used when we have shallower water depths. So it is possible to make a connection up to the seabed. In those situations we will use a bottom supported drilling rig. Now bottom supported drilling rig has platforms, barges and jackups. So these barges are generally used for inland water drilling operations, okay. Suppose you have a lake, in that lake you can use these barges. So it will be towed there using some ships, and then they will somehow sink this barge inside the lake and it will reach the bottom. Then for higher depths like 350 feet, so these barges are used for 20 feet to 40 feet of water depth. So for higher depths like 350 feet, these jackups are used. Now jackup is a piece of equipment which has 3 or 4 legs. So those legs can be pushed inside the water body and they will go and get fixed at the seabed, and when the drilling operation is done, we can again lift the legs and we can tow that jackup from one place to another, okay. So these two are portable. This jackup and barges are portable, and this jackup can be used up to 350 feet. So this offshore drilling, offshore operations, we have another subject based on these all things. So you will understand and study in details about this all in that chapter. So these two are portable, but platforms are generally fixed. In large fields which has very large potential, having large reserves, that means which will give us lots of profit, in those fields we generally use fixed platforms. Now those platforms can be self-contained or tendered. Self-contained means everything is inside that platform itself, but some platforms are small, so some things like the quarters of the employees, they can be tendered or they are placed separately, and the rig operations are done on the platform. So depending upon the size of the platform, it can either be self-contained and or tendered. Now comes the floating rigs. So these floating rigs are used for higher water depths. So when we will have large water depths and unstable conditions, then we can use this floating rigs. So semi-submersible is a very common type of floating rig which can drill up to 6,000 feet easily, and the other type of floating rig is known as drill ship. So this can drill up to 12,000 feet. So drill ship is just like a ship, like any other ship that we see in an ocean or a sea, okay. Now semi-submersible is a type of floating rig which needs different systems to keep it stable. So as there is no bottom support, so we need different systems which are known as mooring system or dynamic positioning system to keep these floating rigs in position, so that they can perform their task, and in case of severe environments we can abandon all activities and move these drill ships and these submersibles to a safer location. So these are the different types of rotary drilling rigs. Okay, so the next topic is effects of environment on the drilling rig. So when we say drilling rig, here we are talking about the mast. So this mast here has to support two forces, we can say. That means two forces are acting on this mast and it should be strong enough to overcome those two forces. So the first force is the weight of the drill strings, casings and other equipments which the derrick has to carry, and the second force is due to the wind. Okay, so as the height of this mast or derrick is very high, about 100 feet, so it will be subjected to winds. So the winds that are blowing perpendicular to this derrick will exert some forces on this derrick. But so let's discuss that wind force. So let's discuss the wind force. So the winds, as they will travel and hit the derrick, some forces will be applied. So generally the derrick will be subjected to less force because derrick is, you can say, hollow, it doesn't have anything in between it. But when we stack here the drill pipes which are kept here when the tripping out operation is conducted, so the pipes will be stacked here, so then some wind force will be acting on the derrick because now they have a cross section area where the wind can hit the derrick. So there is a cross section area where the force or the wind pressure is being applied. Now the pressure of wind can be calculated using this formula. So here this is velocity of wind which is given in miles per hour. So 1 mile is equal to 1.6 kilometer. Okay, so the velocity of wind is given in miles per hour, and the wind pressure calculated here is in lbf per feet square. So it is not in psi. PSI is lbf per inch square, it is in lbf per feet square. So you have to convert this feet square into inch square in order to get the pressure of wind in inch square. Now force, wind force will be equal to, now as you know pressure is equal to force by area, right? So pressure into area will be equal to force. So force of the wind will be pressure into area. Now this area will be the area on which the wind is acting. Now what will be this area? So this is the stack of pipe. Okay, so the height, so this is making a rectangle, so its height will be, let's say, height of the drill pipe itself or height of the stand right? So if they are kept in stand, then the height will be the height of the stand. If they are kept in joints, the height will be the height of joint. So this h into what? Into now breadth. Now how can you calculate this breadth? Now this breadth will be, so each pipe will have a definite diameter, right? So the diameter of each pipe will be same. So if suppose we have 2 pipes, then the breadth will be 2 into d, that means number of pipes into diameter of the pipe, that will be the total breadth, right? So breadth here will be number of pipes into diameter of pipe. Okay, so now the total area will be here h into b, so h into n into dop. So this is our total cross sectional area on which the wind force is acting. The wind force is P into h into n into dop. So h is length of stand, n is number of pipes, and dop is diameter. Okay, so outer diameter of the drill pipe. So you have to balance the units, and finally you will get the wind force. So this was a simple equation which we got from wind force. Now let us try to do a simple problem based on this. Okay, so let's see this simple question. Here the velocity of the wind is given as 100 miles per hour. Height of each stand of pipe is given as 90 feet. Diameter of pipe is given as 5 inches. So if 5 pipes are stacked together, then what will be the wind force acting on the derrick? So they want the wind force. So first of all we will calculate the wind pressure. It will be in lbf per feet square. So that will be 0.04 into, now velocity of wind is given as 100 miles per hour, so put here 100 square. So this was the formula. Now simply put the value of velocity, which is miles per hour. So you will get 400 lbf per feet square. That will be the pressure of wind, right? Okay, now we can convert it into psi by dividing by 144, because 1 feet square is equal to 144 inch square. So simply when you divide it, you will get the pressure in psi. So here the pressure is 2.77 psi. Okay, so now the wind force will be pressure due to wind into cross sectional area, right, on which it is acting. So pressure due to wind is 2.77 psi, right, and cross sectional area will be h into number of pipes into dop, right. So here h is given in feet, so we have to convert it into inches, because below we have inch, right. So convert this into inches. So 1 feet equal to 12 inches, so 90 feet will be equal to 90 into 12 inches plus number of pipes is 5, and diameter of the pipe is given as 5 inches. So this will be our total force. So when we do the calculation, we will get 74,790 lbf. So this is the total wind force which is acting on the Derrick. So this was a simple problem. First you need to find out the pressure which will come in lbf per feet square by using this formula where V is in miles per hour. Then you have to convert it into psi by dividing by 144. Then simply multiply with the cross sectional area. Cross sectional area will be height into breadth, and that breadth will be number of pipes into DOP. This height will be height of the stands. So in this way you can solve this simple problem. Okay, so that was it for today. Thank you and have a nice day.
When your job is drilling for oil, you lead a nomadic kind of existence. You're rarely in one place for long. And every time you move to a new location, you take your drilling rig with you. 800 tons of machinery and a few thousand horsepower to drive it. Setting it all up can take anything from a few days to a couple of weeks. The choice of site for drilling an exploration well isn't ours. It's made by the geologist and geophysicist from their knowledge of the rocks that lie below, 10,000 feet or more. A classic choice would be over a dome-shaped fold in the rock layers, revealed by seismic survey. But in this business, a choice is a gamble. The chance you're counting on is that oil and gas formed somewhere in the vicinity millions of years ago could have migrated into the dome through layers of permeable rock and have accumulated there, hemmed in by an impermeable layer above. Once there, they would have separated, the gas on top of the oil, with groundwater round the flanks, all of them at high pressure. That's what we hope has happened, but it could take 8 weeks or more to prove it. We start with a relatively large bit to drill through the soft surface layers down to 1,000 feet or so. When your target is over 10,000 feet down, you don't just sink a deep hole. You build it carefully, stage by stage. The drill is driven from the surface, turned by a rotary table on the platform. The drill string suspended from the derrick. Down below, the teeth of the drilling bit break the rock into fragments. They'd soon choke the hole unless we had a way of flushing them out. What we use is a special drilling fluid, pumped down the drill pipe to cool the bit and carry the cuttings away, back to the surface. The mud, as we call it, is channeled out over fine mesh screens, the shakers, to remove the coarse cuttings, and then passed through separators and settling pits to get rid of the finer material before it's recycled back down the hole. As long as the drill is turning, the mud must be kept circulating. But every 30 feet, drilling has to stop to add another section of pipe. It's a tough job, and it calls for some slick coordination from the floor crew. But they all get plenty of practice. average well, they'll add pipe over 300 times before they reach the bottom of the hole. Everything's done to a schedule, supervised by the tool pusher. Nowadays, he doesn't push anything but the drilling program. He's responsible, among other things, for ordering supplies of materials as they're needed and making sure they arrive on time. This steel casing, for instance, will be run into the hole when the drill has reached 1,000 feet. It's essential to stabilize the well at this stage to prevent the softer rocks found at shallow depths from caving in. This will be the next job coming up in his program within the next few hours. The casing, like drill pipe, is assembled section by section, and each of them weighs a ton or so. These centralizers are fitted at regular intervals to keep the casing central in the hole as it goes down. The casing is lowered in until it reaches a point just above the bottom of the hole. The next job is to cement it home. The cement is a wet slurry, pumped down the inside of the casing under pressure. Downhole, it flows through the end of the casing and is circulated around the outside and back to the surface, displacing the drilling mud ahead of it. The cement is followed by drilling mud to the bottom of the casing. The pumps are stopped, and the cement is given time to set. Now we can cap the top of the casing with a set of safety valves, known for obvious reasons as the blowout preventers. If further drilling were to encounter extremely high pressure gas, oil, or water, we could have a problem. To contain it, we need a means of sealing off the hole at the surface. It's done by hydraulic rams that close off the gap between the drill string and the inside walls of the casing. As we go deeper, heavier wellhead equipment will be installed to control the higher pressures. Once the blowout preventers are fitted, drilling can continue safely to greater depths. But what if we were drilling not on land, but way out at sea? Our rig might be on a floating platform, anchored 500 feet or more above the drill hole, but we'd still have to follow the same procedures. On a marine well, blowout preventers are every bit as vital, but they have to be fitted by remote control, sent down on guide wires, and locked onto the casing under the watchful eye of the television camera. On top goes a marine riser, a conductor tube to connect the rig directly to the blowout preventers and the drill hole down below. This gives us the closed system we need for running pipe and circulating mud, just as if we were working on land. As drilling goes on, the mud return shows the succession of different rock layers we're passing through. Some of them could contaminate the mud and prevent it from functioning properly, so we need to keep a constant check on its composition. The mud must also be maintained at a given viscosity and density. We don't want it altered too much by the rocks we're drilling through. Frequent checks are also made for any changes in the chemical composition. If we were to hit a layer of salt, for instance, we could be in deep trouble. The mud would cease to do its job, causing the hole to collapse and prevent drilling. We might have to replace the mud with a new supply of an entirely different composition to neutralize the salt. Up on the platform, an equally close eye is kept on the performance of the drill bit. Cutting through hard rock, its life is usually less than 12 hours. Loss of cutting power occurs when the bit becomes dull, and it makes a distinctive noise. Now it's time to pull the whole string, 90 feet at a time, and stack it in the derrick. We can easily have 100 stands of pipe in the rack before we reach the bit. Maybe 4 hours to recover it, another 4 to run the new one in again. Changing a bit is time-consuming, but part of the normal program. But drilling can sometimes encounter problems that are unpredictable. Conditions downhole might suddenly change and affect the consistency of the mud. If it got too thick, it could bind the drill pipe and stop further drilling. If it happens, you just pull out what you can. Then you go fishing, and with luck, you make contact. But if the hole itself collapses, you abandon the jammed-in section and recover the rest by breaking the pipe. You can't drill back down through the blockage. You have to bypass it, using special deviation equipment, offsetting a new hole at a predetermined angle. Mechanical troubles don't happen all that often, but on every well, you have to be prepared for hazards of another kind that may lie buried in the rocks below. A sudden increase in mud flow from the well. Stop drilling and close the blowout preventers. Everything shut down. The pressures are measured, and the pumps are restarted slowly while the cause of the flow increase is identified. We've encountered high-pressure gas trapped in a shallow sandstone. It's flowing into the well and forcing out the mud. Before we can drill on, we have to contain the formation pressure by pumping down a heavier mud. This is usually kept in the storage tanks ready for just such an emergency. At 3,500 feet below, the gas is flowing into the hole. But as the new heavier mud begins to circulate, the pressure is gradually overcome, and the flow stops. As the pressure returns to normal, the emergency is over. With the mud weight increased, we can now drill the rest of the gas zone. Then the hole can be lined with steel casing. Then with a smaller bit, on towards the target. Still a long way to go. As the drill bites through the caprock and approaches the target zone, its progress is monitored foot by foot. Inspection of the cuttings will give us the first indication of what really lies below the caprock, whether or not the choice of drill site was correct. It's sandstone, all right. And it could contain oil. Under the microscope, the sample certainly looks promising. Coarse-grained sand with a definite dark stain. If it's oil, it'll glow yellow under ultraviolet light. It's there, all right, but so far, only a trace. Not until we've drilled all the way through the formation can we begin to assess its significance. To find out more about what's down there, we run a special instrument probe. The probe contains devices which measure certain electrical, acoustical, and radioactive properties of the different rock layers and transmits them back to the surface where they are recorded. As it passes back up through the formations, the nature of the rocks penetrated by the drill and how much oil and gas they contain can be determined by the recorded measurements. Shale, porous sandstone saturated with oil. Even more porous here. Limestone, nothing much in this case. Then the gas layer. And finally, the impermeable shale of the caprock. We know there's oil and gas down there, but there's a lot to do yet before we've any idea of how much can be produced. It certainly looks promising, encouraging enough to justify a flow test. The hole has been cased right down to the bottom and cemented in. A flow tube is now run into the oil zone. To get at the oil, we have to perforate both the casing and the cement. We do it by firing a string of specially designed charges. The oil begins to flow as the pressure in the well is reduced. The flare-off of gas that comes up with the oil signals a successful test. To get this far has cost anywhere from $600,000 on land to $4 million offshore. Yet all we've managed to assess is the potential of the area immediately around a single drill hole. What interests us now is the rest of the structure. To find out the full extent of the oil reservoir, we have to drill more wells. The first outstep has found water-bearing sands, and we can now deduce the profile of the reservoir in this direction. Next, we drill a third well in line with the other two. This again finds water-bearing sands and completes the profile, the shape of the structure, and the position of the oil, gas, and water contacts. But the profile is still only a narrow band of information in one direction across the structure. To round out the picture, we now need to drill further outstep wells at right angles to the first three. Even with a classic dome-shaped structure, outstepping can have its disappointments. Nothing but water, and much lower down than expected. The rocks have slipped along a fault line, blocking off the reservoir. This is what's called a dry hole. But its information was vitally important. We've now probed the limits of the structure, and at last we have a three-dimensional impression of the reservoir. We can now begin to plan its further development. To bring the oil field into full production, further wells will be needed. These are drilled into the oil-bearing zone beyond the edge of the gas, so we get the maximum assistance from both gas and water pressures in driving the oil to the surface. As more and more oil is withdrawn, we can inject water back into the structure to maintain the pressure by drilling more wells outside the limits of the oil accumulation. An oil field may extend over an area the size of a town, with a network of pipelines for gathering the oil and maintaining pressures downhole. If the oil field were offshore, the whole installation, complete with treating facilities and pumps, would have to be concentrated into a very small area. To be economic offshore, drilling and producing facilities need to be located at a central point from a permanent platform. The oil reservoir is then developed to the same pattern as on land by using the technique of deviation drilling. New oil reserves are much harder to find nowadays, but when they are, it's most often in locations that are very difficult to develop. But wherever they exist, and however complex the development becomes, it is our job to reach them, using every human and environmental safeguard possible. Then, to recover as much as we can for as long as we can.